Okay, so so good afternoon to all of you. So we'll start with the diagnostic plot today. So if you just go through the different figures here, it would be very easy. We do the well test to understand the dynamic behavior of the well and the surrounding reservoir area, so that we try to understand the physical nature around the well bore. So what we do generally, we test the well either in a single well, that means to try to understand the individual well, how the well bore storage effect or maybe the skin is around the well bore. Then we go away from the well as we progress in our test. Okay, so then it may be a multi-well test. So in multi-well test, what we try to understand, we try to understand the communication between the well, so that even in case of a producing well or an injection well, we try to understand whatever activity we are doing, is it in proper way we are doing, or the well have certain problems, so that we could rectify the problem and try to do or advance in our activity. So in this graph, this figure is easily giving you some idea. So once we start taking a well test study, so the pressure pulses generated due to either drawdown or maybe the build up, the pressure pulse is generated and it moves away from the well. And so this is what is, that means what we are trying to identify a specific time and the pressure graph, or maybe you consider signals of the pressure with respect to time, so that it gives us some idea about the area where the specific properties are there. So now the same graph I have just put it slightly differently. If you see, the first graph is related to our well, where we get the T1, T2, T3, T4 time. So if you see the with time, you see the pressure pulse is actually moving away from the well. Okay. So what is happening once we take out production, or we stop a flowing well to produce? That means the build up or drawdown. What is happening? We create a pressure pulse, and with time the pressure pulse is actually moving away from the well. Okay, so this is the in terms of time how the pressure is changing. Now in terms of material, if you see the second and third graph, so what is happening, if we are producing Q at the surface, so the reservoir volume would be QB. So Q by QB means how much production is affecting the wellbore or maybe the sand face. Okay, or maybe the reservoir around the wellbore. If you see the graph here, you can see this is the wellbore area. Okay, this line actually. So production, this is production 0.5 and 1. 1 means this area has completely given the support. That means the Q which we are producing at a well at a specific time, that has been supplied at this of that area. So if I just here, if T is fixed in this graph, T is fixed. That means when we are producing at a specific rate or maybe closing it, the area right from this point dotted line to this point is only supplying your material. Okay, so if I just see, that means whenever we are recording a pressure, that means what is happening, this area is already supplied before in the production profile, and this beyond this part where your this ratio is 0, that means that area has not been taken part into the flow. So that means what is happening, with time a specific area is supplying your flow. Okay, so that means this area is not affected to the pressure behavior, and this area has not taken part into your pressure behavior. That means whatever pressure we are recording in a specific time of our test is actually responding, this specific area is responding to that. So this is related to the transmissivity and storativity of that area. That means if you just remember your Darcy equation, Q proportional to P. So that means if we are producing at a specific rate or you are setting a well, that means if the pressure is not following the same value, that means the area has specific problem in terms of either storativity or maybe transmissivity. So now the same graph, that means with time our pressure is changing, with time the material supply from a specific compressible zone is changing, and that is now from radially. If you see in that figure, so that means radially with time the pressure pulses is moving away from the wellbore. So what is the main part what we are trying to get from here? That means if we are testing a well with, because we are recording the pressure response with respect to time. So what is happening with time, actually it is giving us the physical nature of that specific compressible zone which we are recording in terms of pressure. That means if pressure is not maintained or the same with the same Q, that means that area having some deviation from the normal pressure which is either previously or the next domain. So this is what the well test. So what is there? There is a very simple part. We are trying to record the pressure with respect to time, and the time is nothing but how the pressure pulses is moving right from the wellbore to the or away from the well towards the boundary, and each and every time we are recording the pressure which is reflecting the storativity and transmissivity of that specific small domain which is called a compressible zone. Okay, so this is what is the basic principle behind the well testing. Now if we just go into the mathematics of that, so what you see that in case of the assumption what we discussed, single phase liquid is constant mu, C and B. Okay, so that we have, these are the assumption for our mathematical solutions. Formation with constant porosity and H, well completed over entire sand thickness, infinite reservoir containing only one well, uniform pressure in reservoir prior to production, constant production rate Q beginning at the time T0, and homogeneous reservoir. So this is actually what we assume for solving our solution. Okay, so line source solution. So if you see here, this is our solution. That means at specific pressure, the recording pressure is related to the initial pressure as well as certain characteristics of the reservoir as well as the production rate, and the solution which is EI function, exponential integral function. And if you see here, this is the normal part. Okay, so that means this EI function solution to the diffusivity equation assume the line source well in finite size of wellbore can be neglected. Okay, the solution is valid, so I will just discuss. So initially, so that means what the physical understanding is really clear to you now, hopefully. And then the mathematics part, how we are trying to understand the mathematics. So I discussed, this is the X parameter. Okay, X, that means, so what if you see here, the X EI function actually is an expansion. Okay, so expansion is here. I'll just show you, the expansion is here. Okay, so if you see, the X expansion is here. Okay, so what, for different values of this specific X, we generally follow different approximation. So in case of X is large, when it would be large, that means either you have a short time, this means T study is very less, or maybe your radius is very high, that time you will get your X value large. So, or maybe when X would be small, so when your testing time is more and you have the short distance. Okay, so if we just expand this initial diffusivity exponential integral functions, okay, so we see if we follow this is logarithmic EI function expansion term following the expansion algorithm, and here it is the logarithmic approximation. So if you see, we have a specific overlapping domain where X value is 0.01, where X is more than 10 or more than 3. If you see 1, 2 and 3, more than 3 even, that time also we can consider there is no effect of this exponential function. Okay, X. And if so, that means what, for short time X greater than 10, pressure response predicted by EI function is negligible. So in this case, and below 0.01, pressure response may be calculated using the logarithmic approximation of EI function. And when the intermediate times, that means 0.01 to 3 or maybe 10. Okay, so we need to take the really the EI function expansion algorithm. So in this case, you see, when X, that means when X value is more than 10, you should consider your initial pressure is the same pressure. That means that part is not affected. What is the meaning of that? That means the compressible zone has not yet reached up to that part. Okay, the pressure function or pressure signals or pressure zone or the not yet reached to that part. Okay, so that time we can consider P equal to Pi, means that pressure is considered to be the initial pressure. It has not yet affected by the flow. Okay, So next part is your in-between zone when we have x less than 0.0, greater than 0.01 and less than 0.3, or maybe you can say 10. So in that case, what we need to require to solve our solution or solve our pressure value with respect to taking the whole exponential integral expansion. If you see here, we have the tabulated form, everything is there depending on your x value. Okay, x is, you can use this graph. So here you see x is equal to 0.05. so what you do, 0.0 up to 2 you take, then here you are getting the next term, so 5.2. so up to this you can take, so this is the value, so 5, so this is 1 and this is 2, so you are getting 2.431. so that is how, when specifically we have the value of x greater than 0.01 and less than 0.3 or 10, that time we could really use the whole expansion parameters. And when long time approximation, when your x value is less than 0.01, that time you see the logarithmic approximation as well as EM function having the same, they are overlapping. So that's why that time we need to use the logarithmic approximation of pi. So P is pi initial pressure with your logarithmic approximation of our x value. Okay, so that is how we could just use our approximation value to get our pressure response properly. So now these are all related to, so this is what we know, the relations between the dimensionless pressure and our normal field values, field unit. This is dimensionless radius. This is dimensionless time, how related to T, this is dimensionless pressure. So once we discuss in terms of this diffusivity equation in terms of the dimensionless form, it would be this. So combining all these equations and solving explicitly for real pressure, any point in the reservoir located at the distance r from the following well at a constant rate q, this is actually the whole exponential functions, and once we are solving the value of x is in between a specific range, we can use the logarithmic approximation. So this is the mathematics behind it. So now using this mathematics, now what our role is to solve it. So how to solve it, or what should be the different slope of the graph or the pattern of the graph, so that we could identify or we can diagnose what is actually the physical nature around the wellbore at that specific flow time or that specific time. Okay, so flow in fluid in the reservoir flows in different ways at different times. Okay, this is often a function of the shape and size of the reservoir. The basic flow designs are categorized in terms of which time region they occur. So we have understood around the well, okay, so around the wellbore, then it is moving to a normal reservoir area, then it is now getting the response of the boundary. So what it is, very simple response, you see here log, del P and derivative both are there, and here all the pressures are there. Okay, so if you see the pressure, so you see the pressure is gradually changing. So that means generally in most of the cases what we do, we del P and the particular derivative is used to identify a specific domain and how their behaviors are. Okay, so what is there, we need to understand the physical phenomena around the wellbore, how the pressure response would be reflected on the flow. Okay, so this is what, this is normal pressure versus time. So if you see here, you can easily understand. So in specific, so these are the domain where you actually cannot understand what is happening. But if we simultaneously plot in a diagnostic plot, that means del P and derivative in log plot, then we can properly characterize certain domain to understand what is the early time effect and how the physical natures are. These are very important part. So now what people are trying to understand, though you may not get a straight line, but you can get a curvilinear pattern so that you could understand what is the pattern. Okay, so early time, so if you see here, last class also we discussed this graph, and we discussed about the, and there's a dotted pattern which can give you some idea. So where the this is actually transient state, where transient means the transient has not yet reached to the boundary. That means it is still, we discuss an infinitely acting reservoir, and this is the starting of your transient. So in this specific pressure del P versus, it is not possible to identify where your transient is ending, but if you plot it simultaneously, you can easily understand. You see here, it is a slope is moving up, but once you come here, you get your derivative plot having a zero slope. Okay, so this is your transient state, which is called the intermediate state or the main domain of your reservoir. Then again you see there a deflection of your curve. So one is steady state, another is pseudo steady state. So we'll discuss how the volumetric flow is supporting to get the behavior of the pseudo steady flow, then your early time or maybe the Weilbur-Story effect, the skin and everything. Okay, so now so this is what we generally discuss. Okay, so this is what the same graph, if you just follow, so figure provided us with an example diagnostic plot. So in diagnostic plot, what we do, time in hours, we put it in the semi-log log plot. So here also the log part. Okay, so log plot, if you see, the pressure is changing in a specific part, but this specific pressure may not help us to identify certain things. But here when you do the derivative, so each and every area has giving a specific part. So what today we will try to discuss particularly the state line domain. Here you see, we discussed in the last class also when we are discussing the type curve analysis. You see a zero value of this value, one value is going somewhere, and then if you see some value coming here and some value coming up. So if it is below, that is the stimulated well. If it is above, that is actually the restricted well, or maybe sorry, stimulated well, and that is maybe your flow may be supported from somewhere. It is not following a zero. It following maybe the one slope, but it is above this slope 1. Okay, so early time region is the Weilbur and near Weilbur effect dominate. So today we'll discuss only the straight line nature, but maybe for subsequent class we'll discuss further to understand early time again around the Weilbur for different type of features around the Weilbur. So this effect include Weilbur storage, formation damage, partial penetration. We discussed how actually the Weilbur support or Weilbur restriction is due to a near Weilbur characteristic of a well. So if I just see here, if you see this is an intermediate domain. Okay, so what is the intermediate domain? Here you see intermediate domain is coming from here. Okay, so infinitely acting reservoir part. Okay, so closed circle. So this is actually closed circle boundary. If you see here, this part has been omitted maybe, or maybe data has not been recorded properly. So middle time region at intermediate times, a reservoir will ordinarily be infinitely acting. So this part also again we'll try to understand, because here we are considering an homogeneous reservoir and the support is very good and it is following a zero slope line in derivative graph. Okay, in everywhere you see here, in this case radial flow. But we'll see afterwards by different way, different types of main reservoir, this graph will also not follow a straight line. Okay, so maybe in the subsequent class. So for homogeneous reservoir, the pressure derivative will be horizontal in this region, lead to accurate estimation of permeability, formation permeability. So this is what here you see that your transient has started in the normal reservoir part, so the derivative slope is 0. Here is the same part, but after that you see again you are getting a deviation. Okay, so late time region boundary effect, dominant curve shapes. This type of boundaries that may affect the pressure response include ceiling faults, closed reservoir, gas and oil. So these are different type of boundary you may have. So what if we just distribute it again, going back to this graph? Okay, so what you see here, this is the early time region. So early time region, we got a graph like this, but we may get different shape depending on the formation damage, partial penetration, phase distribution, stimulation, fracturing, fractured well. Okay, so that also may vary. So this is a very simplistic form having the basically volumetric reservoir support, or maybe volumetric Weilbur-Story support. Next part is your middle region. That is also straight line, because we are considering this as a homogeneous reservoir, so that's why here the pressure is changing. But if you see a derivative, that means it is a in semi-log we got a straight line domain, but in case of derivative log plot we got a horizontal slope. That means it is homogeneous reservoir, and or maybe you can say infinitely acting domain. Once we go to the late time region, that means again the support is not proper. Okay, so that means you may have a pseudo steady state, and we will discuss this graph, and this graph everywhere is giving us some idea about what is the support system existing into the reservoir. Okay, so that means we have mainly 3 domain. One is near Weilbur area, another is infinitely acting domain, and the third one is okay. So now what is volumetric behavior? Volumetric behavior is defined as that pressure response time is dominated by wellbore, reservoir, or part of the reservoir acting like uniform pressure, tank with fluid entering or leaving the tank. So that means we have a tank having a specific fluid filled into the tank, and now you are taking a production or maybe closing it so that the tank will fill, or maybe it will basically release or maybe evacuate the fluid, okay, releasing the fluid at a specific rate. So that means volumetric behavior is nothing but it is behaving as a tank which is a specific volume, and we are now producing from that specific volume. So depending on the compressibility value of that particular fluid, it will follow a straight line. Okay, that means that is what is called the volumetric behavior. So the most common example of volumetric behavior is wellbore storage, which dominates during the early time region. The tank is the wellbore in which the pressure is uniform. So what we discussed earlier also, that means the wellbore storage is wellbore volume of the fluid is considered to be the tank, and when we are taking out from it the specific rate of production, that means it is supporting from the tank, and what that time we are considering the sand phase where the perforation has not yet supported anything to enter it from the reservoir. Okay, so that is what is considered to be a tank model, or you can see that's why what fluid either leaves this tank earliest time in the flow test before the reservoir begins to respond, or enters the tank earliest time. So what we are considering, this area is specifically, you see when it is leaving, we discussed the compressible zone has moved directly from the tank to the tank and skin, or you can the sand phase. Okay, so this is what when we are producing from a wellbore, that time it considered to be a specific tank of having a specific volume of fluid, and we are producing it, that's why it will follow a specific straight line. Okay, so and we discussed earlier also what is wellbore storage. So up to that, that means it is strictly a wellbore storage effect, and when it is leaving, that means it is now combination of both. What is that? We have the the wellbore storage effect as well as the skin. That means sand phase is now allowing the fluid entering into a reservoir and supporting your flow, but not that strict way. So that is what this part. So 1.5 log cycle after the leaving of this straight line graph is considered to be the up to that the wellbore storage effect is dominant. Okay, so that we have discussed. So straight line is giving us the unit slope which is considered to be strictly of wellbore storage effect. Okay, and when it start leaving, 1.5 log cycle is considered to be the end of the wellbore storage effect. Okay, so now volumetric behavior, you see the second line of straight line here also the same. So another example of pseudo steady state boundary dominated flow in the closed reservoir during constant rate production. So what in this case, the reservoir is a tank, that means the whole reservoir is considered to be a tank. Now in the boundary there is no support, that is called pseudo steady. That means at specific rate the pressure will decrease, there is no support. Okay, so the pressure is changing at the same rate throughout, it is not the same at all points, and fluid is leaving the reservoir to the producing well. So what we are considering, that means here we are considering up to this. So initial part, this is the wellbore, and this is the part, that means the whole reservoir is considered to be a tank and no support from the external boundary. So that's why what we are getting a pseudo steady behavior having a slope line 1. Okay, so that means at a specific rate the pressure will decrease. Okay, normal part. So what is happening, this reservoir may behave like a tank with recharge fluid influx sometimes entering from secondary source of pressure support, such as, so what it is there but not in that rate. So if you see here it is supporting, okay, completely, that's why you are getting, but if it is supporting in the same rate, you should follow the same line, but it is not supporting at the same rate. Okay, so that's why it is not following the same line. That means when your production at the Q and from the influx from your specific aquifer is same, then you may get a straight line will continue. But if it is not that means you have some half-hearted support, so that's why we are getting that means a specific rate it will be decreasing, okay, and that is depending on the rate and the volume of reservoir fluid inside your whole reservoir, okay. So what is happening, entering the from secondary source of the pressure support, such as large supply of hydrocarbon in the lower permeability medium in pressure communication with the reservoir being tested. So it may be an aquifer, it may be from another source, maybe another support, okay. So then what is happening, if you see here we have one unit slope and here you have another unit slope, and this slope is completely dependent on the nature of the fluid, okay. So that means here we are considering the wellbore is only the tank, and here when it has reached to your boundary or the main reservoir has been now not supported by the maybe the aquifer or maybe aquifer, so that means we have a half-hearted support, that's why we are getting another slope and the pressure is decreasing at a specific rate following a specific pattern which is a unit slope, okay. So this is two domain of our infinitely acting reservoir, and then okay. So another example of pseudo steady state flow in the closed reservoir during constant rate production. So in this case the reservoir is the tank, pressure is changing at the same rate throughout the, okay. So that I have already discussed this graph. So now, so this is the two part, okay. So this equation, so now if we are going our earlier formulations of your pressure and how it is related, so this is what this equation modeling wellbore storage, okay, derived from the mass balance of the wellbore. So this is no way related to other particular parameters which are involved in this pressure test, because what we discussed, this del P is only supported by the fluid inside your wellbore. That's why the C, Q, B and T, you see this is the production rate and other no formations or maybe the formation characteristic involved with this. So this is only related to, so what we are now having a specific equations, but once we are going into this domain, pseudo steady state domain, the equation modeling pseudo steady state flow in the cylindrical drainage area. So if you see here, this is actually the graph which is here, okay. So what Pi minus PWF we discuss, this is a logarithmic approximation and this is the formulation. So what we are trying to get the pressure change with respect to the flow behavior with respect to reservoir parameters as well as the flow rate, okay. So this is two part. So if I just put, so general form of your this is what the general form, okay, of our y equal to mx plus c. So del P is your 1 and this is your y equal to mx plus c. So this is what your BV, bulk volume, and this is your particular formulations and the derivative. So what, this is one part which you are plotting in the left side y-axis, and this is another value del P by del T we are plotting in our x-axis, and y-axis we are trying to get the time in form of, okay. So the implication is that the derivative plot will have the unit slope on log-log cycle as it moves over one log cycle on log-log coordinates, and the pressure change plot will approach unity at long times when the bulk volume is not equal to 0, okay. So that means we have two proper characteristics here. If you see, this is actually the pressure response and this is the derivative response, okay. So that means in a wellbore storage BV is 0 and the derivative, the pressure change plot will lie on the top of another. So if you see here in this particular wellbore storage effect, both the graph having the same slope, but during the pseudo steady state flow or recharge, the pressure change and the pressure derivative plot will not coincide. So if I just go back in the graph, you can easily see here it is ascending, but here more or less both having the same slope and they are overlapping one another. But in this case, you see this is the pressure response and this is the pressure derivative. So they are not same. So this is how we could understand a volumetric behavior in terms of the wellbore storage effect as well as in the pseudo steady or in the boundary domain. Okay. So now next part is radial flow. What is radial flow? In case of infinitely acting domain, so where radial flow may occur. So this first we have to understand what are the situations available for having the radial flow. So if you see infinitely acting radial flow is common in reservoir. So what if you just try to remember, we have a wellbore, then we have a pay thickness, or you can see the H thickness of a pay zone, we perforated all through sections. So and the data in the radial flow design can be used to estimate formation permeability and the skin factor. Okay, so what we have discussed about the normal KH, and then using the KH we use it for the skin determination. So common situation, if you flow into a vertical well after wellbore storage, distortion or skin effect distortion is seized and before the boundary effect. So if it is an homogeneous reservoir, then what we consider this after the skin and up to the boundary effect, we consider it's a radial flow. Okay, that means infinitely acting domain is considered to be radial flow if the reservoir is homogeneous in nature. If not, we will discuss in subsequent section how their graphs would be. Okay, hydraulically fractured well after the transient has moved well beyond the tips of the fracture. We will discuss this is up to a hydraulically fractured well. It considered initially bilinear flow, then it will be an elliptical flow, then it will move to a transient. That means the transient area has moved well beyond the tips of the fracture. Okay, so we'll try to understand afterwards with the configuration or diagram, so that what then you have a wellbore around or fracture around the wellbore. Initially you may get certain part which are related to your linear flow initially, then you may get the bilinear flow, then you may get the elliptical flow, then you get the radial flow. Okay, so that means what each and every part we may have a slight difference in our shape of the graph. That we will discuss in the subsequent section, not today or maybe next class. Okay, horizontal well before the transient has reached the top of the and bottom of the productive interval. So if you have a horizontal well, so now what is there? In horizontal well, you may have also skin effect, you may have also the wellbore effect, but after that, that means the transient has reached, that means the compressible zone. What is transient? Transient is considered to be the compressible zone. Okay, so it's always similar. Transient means it has not yet reached to any steady or semi-steady or pseudo-steady state. That means it is still not reached to the boundary. Okay, that means where the compressible zone are. So compressible zone, that means the transient has reached the top and bottom of the productive interval. Okay, then horizontal well after the transient has moved beyond the end of the wellbore. That means wellbore. So this is what in between. So wellbore effect. So that means what is happening? We try to understand how they will behave. So the same equations, you see that equation used to model radial flow for well producing at constant rate is similar logarithmic approximation to the line source solution. This is the same what we discussed earlier. So this is logarithmic approximation. We consider the skin parameter. So this is what our, okay. So now this is what. So now if you see, we are trying to put all the formulation, particularly the del P in terms of y equal to mx plus c, and here also the same. Okay. So what if you see here on the diagnostic plot, radial flow is indicated by horizontal derivative. So we discussed earlier, so pressure will change, but that will not demarcate where your transient or maybe the radial flow has started. Okay, so this is what we are trying to understand when we have homogeneous flow from the reservoir, then how the shape of a pressure change as well as the derivative look like. So whenever we are getting any horizontal flow, that means this is considered to be a radial flow. We will discuss, but the radial flow is sometimes following a 0, sometimes 0.5, sometimes 1. So that we will discuss in the subsequent section. Okay, so this is radial flow. Okay, then we are coming into the linear flow. Okay, so what I thought I'll stop here, and we may stop our recording and we'll discuss our things. Okay.